this is the last chapter which is going to cover in the midterm examination. Okay, so see this one, girls. By the way, this is a different chapter in the sense that before chapter what you learn, it is basically DC circuits, direct current. And now we are going to start the AC, introduction of the AC, which is alternating current. And hope you know the difference between AC and DC. Not much, but little bit you should know. Like the power supply at your home, okay, where you connect all your appliances like TV, fridge, or laptops. You are connecting other appliances, washing machines, and all you are connecting. Supply, all the household things are basically run on the AC supply, okay, alternating current supply. While the DC sources are, direct current sources are, that the batteries which we use in the toys, batteries which we use in the mobile phones, in the car, okay, and these are the sources for the direct current, okay. And direct current is basically provide the constant value, okay, of the voltage. And alternating current is just the name being alternate. It keep on changing. Okay, this is about that. So just a minute. Okay, so as the name said, was alternating current, yani you can see here, it is basically the sine wave. Hope you have idea of the sine function. The sinusoidal waveform is basically a sine wave, which is a fundamental alternating current AC and alternating voltage waveform. Okay, alternating current or alternating voltage waveform. Shape is same. So you can x-axis we have time, on y-axis we are having either voltage or current. So above the zero axis it is positive, below the zero axis it is negative. So you can see with the time the value is keep on changing. You can see this one, it is keep on changing. Okay, so it is consist of one complete cycle. What is a cycle? It is basically a combination of one positive maxima, one negative maxima, yani this one cycle, positive half, negative half, which give us a complete cycle. So it's keep on changing and return back to the same value. So this is a sine wave. So it consists of positive maxima here at this peak, and it consists of negative maxima here. So an electrical sine wave are named from the mathematical function with the same shape. You know that sine function or sinusoidal wave is given this one. Okay, now and I also mentioned that it is same shape for the alternating voltage, or it is same shape for the alternating current, except on this axis either voltage or current will be there, and this is the time actually. So what is a wave basically, guys? So wave is a disturbance. Unlike water waves, electrical waves cannot be seen directly, but they are similar characteristics. Okay, maybe you have noticed that when you are sitting near to the water, maybe in Cornish or somewhere, if you throw if you throw a stone in the water, you can observe such type of waves. Can you see? Have you noticed this one? These waves are basically which which we can see, but electrical waves you cannot see. But both electrical wave or this water waves have similar characteristics. Okay, so all periodic waves, periodic yani the waves which keeps on repeating itself after a fixed interval is called periodic. So all periodic waves can be constructed. What is that? Can be constructed from sine waves, which is why the sine wave are fundamental. So the last line, the end of the chapter, I'll show you how with the help of this sine wave, how can we construct other periodic waveforms, which is why sine wave are fundamental. So sine waves are fundamental waveforms, and by using the sine wave, we can generate other type of waveforms. I'll show you at the end of this chapter. So see now. Sine waves are characterized by amplitude and period. So there are two things in this wave, amplitude, another thing is the period. So the amplitude is the maximum value of the voltage or current. The period is the time interval for one complete cycle. See the amplitude, where is the amplitude? So amplitude is measured at the center of any peak, okay? Here you can see this is the center, and what is the peak value here? So if you try to understand this one, this is 20 because this distance at the center of this peak is 20. This is called amplitude. All right. It is also called peak value. Why peak value? Because this is the maximum voltage or maximum peak voltage at this point actually. So of this wave, okay, it is also called peak voltage. Now we can see the period, yeah, highest point, which is peak, correct. Now the period yani a period is the time interval for one cycle. Yeah, it is gonna be 50, but 50 is just a number. Yani 50 apple, 15 banana, 15 real, $50, what? 50
microsecond.
Microsecond. Yeah, you can see on the axis the unit is mentioned. So without unit, it's nothing, it's just a number. So 50 microsecond means is that in 50 microsecond, this wave will complete one cycle. Yani start from the zero, go to the maximum value positively, come down, reach to the negative value and become zero here again. This is called one period. All right. So it's so easy to identify. This is 50 microsecond. Now, so sine wave period, girls, not only measure from this 0 point to another 0 point, which is 0 to 0, we can also measure at the different corresponding points. Actually, what are the different corresponding points? It could be like we can measure from positive peak to the positive peak. Yani, this is the one. This center exactly, and here we can exactly measure. This is peak to peak again, which is time period. I can measure from this minima to this minima, all right, corresponding, right? So this is also give us, time period. I can also measure negative peak to negative peak again, corresponding negative peak. It's also, so you can measure time period at a different points, but what are given here, okay? This is what we call time period and how can we measure it at different points. This is the way. Now, so by contrast of amplitude of sine wave is only measured from the center of the maximum point. So we can see that it can measure, time period can measure from the different corresponding point, but the amplitude must be measured from the center of maximum point. Yani, I can measure amplitude at this point only. If you look here, what is the amplitude? You can see 0. If you go here, how much is the amplitude? 0. If you go here, 0. Okay, so this is though is exactly same amplitude, but it is negative. So it is always measured at the center of the peak. On the other hand, time period can be measured between two corresponding points as shown in this figure.
Doctor?
Yes.
يعني when we want to find the time, we will minus the peak 2. from big 1.
Okay.
We will minus to
No,
find
again,
the period.
what you said, yani measure this one time period, right?
Yeah, time.
So
Big
time
2
period,
from big 1.
2 points. Yani you can measure here to here. This is
Yeah.
possible.
لا لا
Okay.
دكتور we will minus ولا divided ولا what?
No, just measure. Yani count how much is there. Yani you can say, for example, here is, let's suppose, I am just giving the points. This is 1. Okay, this is 2. This is 3. Not here. Yeah, it is 3. It is 4 seconds. Okay, let's just take it seconds. Okay, and you know that what will be the half. If I go here, it is 1/2. Yani it is a half, right? 1/2. And here it will be 1.5 or 0.5, like that. Okay, so I want to measure it basically. So what is the point here? If you look, it is 3.5, or here is 1.5. So if you subtract 3.5 minus 1.5, you will get it. So 3.5 minus 1.5 will give you 2 seconds. Yani 2 seconds. Now, if you want to measure here, okay, you can measure from here to here. It is direct because it is starting with the 0. So you can say 2 minus 0. It will give you 2. Similarly, if you want to measure from here to here, so this point is 2.5. So you can see 2.5 minus this point is 0.5. So it is what? 2 again. So you will be getting 2 everywhere. 2 seconds. Clear?
Yes. Yeah, clear.
Okay, welcome. So this is the time period. All right, now another thing is here frequency. See, in this chapter, girls, you will see the formulas. Those are very basic, very easy formulas, and you can easily score the marks for this chapter because of it's just formulas, and you can just put the values and calculate it. So next thing comes, which is frequency. So what is a frequency? The frequency is denoted by a letter F and is the number of cycles that a sine wave complete in 1 second. Yani how much cycle a wave will complete, a sine wave will complete in a second. We will say it is the frequency of the sine wave. For example, if 10 cycles, yani complete positive and negative, 10 cycles are completing in 1 second, so I will say the frequency is 10 hertz. Hertz is the unit of the frequency. Understand? Hertz is the unit of the frequency. Yeah, so see now, if 3 cycles of a wave occur in 1 second, the frequency is, so you can see here, it's so simple to understand. This is 1 cycle, another cycle, another cycle, 3. So it is gonna be simple 3 hertz because of, okay, this point. So more the frequency, more closer these cycles will be. When we say high frequency, yani it will be more closer. So it means more cycles can be there in 1 second. And the processor, your processor, when you purchase a laptop or the frequency is mentioned, how much it is mentioned, around 2.5 gigahertz processor, gigahertz, right? What does it mean? Can you imagine? You can say frequency actually is related with the time period. You will see in the next slide, but I am mentioning here, so I will clear it this point here. The frequency is related to the time period this way, 1 over t. Okay, or we can also say t is equal to 1 over f. So time period and frequency are related inversely, okay, inversely proportional to each other. So if this is the frequency and I ask you calculate the time period, so you will say 2.5 into 10's power minus 12, because gigahertz, right? Is it 12 or 9?
9.
9.
9. Yes, it is 9. Okay. 9 is giga. No, it's not negative. First of all, it is positive. Okay. Okay, so like kilo, mega, giga, 9, correct. So when we will flip it, you know what you will be getting? 2.5, and it will go up. And how much it will be? 10's power minus 9, correct? 10's power minus 9, which is now nano, correct? So 1.25 means 0. How much it will be? 1 over, so 1 over 2.5. 1 over 2.5 will be 10 over 25.104, 0.4 nanosecond. 0.4 nanosecond. What does it mean? 0.4 nanosecond. It means is that one cycle is so short. It is now completing in 0.4 nanosecond. Can you imagine the nanosecond? And now it's 0.4, 0.4 only nanosecond. So it means it is so close. One cycle so close, very dense, very dense. It's like that. So it is something, high frequency means the signal means waveforms will be very close to each other. It means is that. All right. So just for your information that frequency and time period are closely related to each other. You can see here. Okay. So F is equal to 1 over T, or T is equal to 1 over F. Now, if the period is 50 microsecond, the frequency is, so it's so simple. You can say F is equal to 1 over T, and it will be, how you will be calculating this one? Simply F is equal to 1 over 50 microsecond. All right. So yeah, it is gonna be either 0.02 megahertz, or we can convert it into kilohertz. How can we convert? Any larger unit to smaller. You know that one, if we multiply this one by 1000 and just keep the 10's power 3 here, because mega means 10's power 6, correct? So it is gonna be 20 kilohertz. It is gonna be 20 kilohertz. It means is that. All right. So it's you can just change the units. You know that one, how to do this one. So this is the frequency. All right. Now sine wave voltage and current values. So see now guys, as I already mentioned to you, amplitude is also called as peak value. What is called peak value? Yani the maximum value of a waveform, which is also abbreviated as VP, yani peak voltage. Similarly, I can say IP, yani current peak. This is peak voltage. Similarly, peak current, which is IP, we can say. So both are same. Either I'm talking about the voltage, I'm talking about the current. So I'm explaining VP, IP, you can understand in the same way. So see now. So if I ask you what is the peak voltage of this sine wave, so it's so simple for you. You can easily say, okay, at the center, at the center, you will check it, the maximum value, which is 20 volts. So you can say the peak value or the amplitude is 20 volts. All right. Now, another thing is that it's about peak value, peak voltage or amplitude is same. All right. Now, another thing is that, guys, because in sine wave, as you can see, what you can see, it's keep on changing, right? Keep on changing. So how can we find its equivalent value of the DC? Sometime it is required. We need to calculate its equivalent value, because if we just get the average of this signal, you will get 0. Why? Because it is the positive value, and below that we have negative value. It will cancel each other and will be getting 0. So there is a term which we call RMS value, root mean square value. Okay, so for that there are some link, you can go and check it in more detail. The RMS value of a sinusoidal voltage is, now see this one, is equal to the DC voltage. Yani we can also, you can say, find equivalent DC voltage if we get the RMS value. So it is equal to the DC voltage that produces the same amount of heat in and resistance as does the sinusoidal voltage. So you can convert the peak value of the sine wave to the corresponding RMS value by using the following relationship. So if you know the peak value, girls, you can convert it into RMS value. So similarly, if you want to calculate IRMS, you must know peak current. So if you know the peak current, you can calculate RMS. If you know the peak voltage, you can calculate the peak RMS. So this is the formula for that. By the way, this formula can also be written as VRMS as VP over under root 2, which is I remember always, because rather than memorizing the number 0.707, it's easy for me to memorize VP over root 2. Can you check it? 1 over root 2 will give you 0.707 or not? Just check it. Yes, so it's gonna be easy to memorize rather this number, correct? Okay, so it's this way. Similarly, you can calculate IRMS. So what you will be writing? IP, peak current.
Yeah.
Yeah, over
Root.
bus. This is the way. Yeah, it is constant number because 1 over root 2. This is 1 over root 2. Okay, but you need to multiply by the VP. Now, similarly, guys, this formula is sufficient itself. So if I give you RMS value, you can calculate the peak value also. So VP, I can say what? Root 2 multiply by VRMS. Okay, now either they are writing this way in the book. So you can also check it. Root 2 value is 1.414. Check it this one as well, so that you will be sure that yeah, it is gonna be same, correct? So it means this way we can easily memorize the formula, and you just memorize for voltage, current is exactly same. You need to just replace V by I's, correct? So this is the one formula of the RMS. All right. Now, sine wave, current value. Yeah.
I have a question.
Yes.
What the problem? It will be to do this solution. Maybe and something like that. And how we can find ID?
How you can find IP?
Yeah.
Okay, so this is the peak value of the current. Maybe it will be mentioned to you in the question that for the given peak value of the current, calculate the IRMS value.
يعني دكتور, it will be in the question.
In the question, yeah. Yeah. It will be there, or maybe we can give you this waveform. We will say this is the waveform. This is the peak value is 20 ampere. This is ampere. So it is given to you already. So from this graph you can get it. Yani IP is 20 ampere. So khalas, you just put it in the formula and you can calculate the IRMS value.
يعني دكتور يا اما VB يا اما I. So
See,
we will find يا اما VB or
IP. Both are same. Yani it's not like it's depend upon the question. Which waveform is this? This is current waveform. Current, because this is mentioned here ampere. If it is voltage waveform, so here what we will be having? Voltage.
Okay.
Okay, but this is the difference only. So if this is voltage, you can get VP. If it is current, you can get IP. That's it.
Yeah. Thank you.
Yeah, all welcome. So both shape are same actually. Shape is same. But what is given, you need to check it, whether voltage or current. Okay. Now, and next thing is added here, which is peak to peak. Yani one peak to peak. Now you can see, girls, peak to peak is what? So this is the positive peak. This is the negative peak. Okay. So if I measure from here to here, you can see that it is just a this measurement here. And how you will measure? This is 20. Okay. Minus this is minus 20. So how I will be writing? Minus 20. It means 20 plus 20 is equal to 40 volts. So peak to peak is basically the value from one peak to the another peak. This is peak to peak. Or see, can I say that peak to peak, yani VPP is equal to twice of the VP. Is it same or not? Can I say this way?
Yes.
Correct? Yeah, it leads to new formula. Yani VPP is equal to 2VP. Now, if I ask you calculate the root mean square value, so I can say Vrms is equal to VP over root 2. Correct? Or I can write in terms of VPP. How can I write in terms of VPP? Get it VP value from here, which is VPP over 2, which I can put it there. And I can say this is VPP over 2 root 2. Can I write this way also or not?
Yes.
Okay. So it's just they are related, but you must know the what is the relation between them. So it's simple. VPP, yani peak to peak is equal to twice of the peak value. That's it. All right. Okay. Now see this one. So they are asking what is a peak to peak voltage. You can easily calculate. It is 40. All right. Now, if they ask how much is the RMS voltage, so RMS voltage, there are two ways now. Either you can apply Vrms is equal to Vp over root 2, or the another one formula which I just derived for you, this is Vp over Pp over 2 root 2. It's up to you which one you want. You can apply both of them. Okay. So if you apply this one, so according to this one, it is going to be 20 over root 2. And if you want to apply this one, it is going to be 40 over 2 root 2. By the way, both are same. You know that. Okay. Same answer you will be getting here. Okay. Yeah. So this is the way. Now 14.1 we will be getting. All right. Next thing is come here, girls, which is called average value. Now, what is average value, girls? Average value, the average value of a sine wave when taken over a complete cycle. See, if we go for the complete cycle is always 0, because when you got the average for this positive cycle, it is gonna be cancelled by this negative cycle because it is exactly equal but opposite. So if I go for the average value of a complete cycle, I will always get 0. You know this one, right? So in order to get the average value, we will not take this complete cycle. We take it at the center of any peak. For example, the average value, if I want to calculate, so I will say V average is equal to VP, yani at the center, we know the peak VP over what is the angle here actually. See, girls, in order to complete this complete cycle, which I will show you here in the next slide, but I am mentioning here, complete. You know how much a degree in, what you call angle, how much degree in degrees it will take? It takes 360.
Yeah.
Yeah, all right, 360. Okay, to complete it. Yeah, no, 90 is this one, phi. Maybe you are talking about the peak value. Okay, so complete is 360, and if we go for the half cycle, it will take 180 degree, and the center is gonna be 90 degree. Correct? This is something in degrees. If I want to write in radians, it is again interesting. What is radian? Yani up to here, it is gonna be 2 pi, and here it is gonna be just pi.
Pi.
Yeah, at the center it is gonna be pi by 2. Correct? This is the way. So you will see in the next slide, I will explain these things also. So here, in order to know the average, as I told you, we will look only the at the center of any peak, and we will find the average. So the formula is V average is equal to VP, because at the center the value will be the peak. And what is the angle in radians? So that is pi by 2. This is the formula for the V average. So I can say 2 VP over pi. Can you check it? What is 2 over pi? You know the value of pi. This is 3.14. So just check it whether are you getting the same value which is here or not. 2 over pi. Because VP is already in multiplication, which is there as well. So what is 2 over pi?
Yeah, the same.
Same number.
Same number. Okay. So which is easy for you? This number or this way? Yani VP over pi by 2.
The number.
Okay. So it is up to you what you want actually. And Gus, do you know 2 VP? Do you remember anything? Twice of the VP? What I can write it?
VPP.
Yes, so I can also say VPP over pi. This is also possible, okay? So they are related, but you can go here, there, whatever, but you can find it. So again, I taught you an easy way to memorize the formula this way. Now, if this waveform is the current waveform, so only thing will be I can write I average, and definitely I will use the peak value of the current over pi by 2. Or I can say 2IP over pi. Same way, exactly same way. Depend upon what is given to you, whether current or voltage. Clear? Any question?
Clear.
Okay. Yes.
Yeah. Question. Okay. Doctor, when you
Yes.
say B RMS is equal BBB over 2 multiple يعني square of 2. How we find 2 multiple square of 2? How we find 2 يعني بسرعة. Understand?
By the calculator?
لا دكتور. Can I write it, please?
Yes, okay, okay, right. Let me remove this all, what I wrote it. Now then you can write. Yeah.
Listen. Okay. It's equal to BB and 2. Yeah. How we find? Okay, I want, but I know, but it's 1, 2. How we find 2, يعني 1 and 2? How we find it?
1 and 2. No, you know this is square root, which is there in the calculator function. First you put 2, then there is a button in the calculator for the square root. So you will get the square root of this one. And the square root of 2 is how much it is? If you remember 1.414. This is the value of the square root. Then you are multiplying with the 2. It is in the multiplication, dear. This is in multiplication. This is. So when you multiply this value, you will be getting here value. So it is going to be how much? 2.828. That's it.
لا.
Clear?
how we put this any rule is يعني all rule. Okay, 1 minute. Yeah, this rule B, okay, R MS equal to VB over. Yeah, this rule is okay, but how we find we went to
Okay.
okay?
Okay, I
Understand?
got your point. Yes, I understand, but you did not understand. So I will understand you 1 minute. So as you said, yani VRMS, you know already it is VP over root 2. You know this one, but
Yes.
you want to know how this is coming. RMS is equal to VPP over 2 root 2. Okay,
Yes.
correct?
Yeah.
So how it is coming? It is coming from the relation. What is the relation? VPP is equal to 2VP. Do you know this?
Yeah.
Okay. So can you find here VP value? How much it will be VP?
It will be VPP over 2.
Over 2. Bas khalas. Can you put this value here in this equation?
Yes.
Not
VP.
not this one. Sorry. This equation. This one here. Because here is VP. So when you put this value VP and this is the VP value. So we will say this VPP over 2 over under root 2. Clear?
Yes.
So this this root 2 will come down and we will be having VPP over 2 root 2.
Yes, Doctor, I understand it. Thank you.
Easy?
Yeah.
Okay, so I explained this one at that time, how it is gonna be there. So this is the way it comes from the relation. You don't even remember, you can first calculate the peak value and put in the formula. Khalas. All right.
Yes, Doctor. Thank you.
Okay. Okay. So now this is average value, girls, and the formula for the average value I explained to you. Now, so for some purpose, the average value, actually the half average of the wave, is used to specify the voltage or current by defining the average value is this time of the peak value. Now, the average value of the sinusoidal voltage is, so if we are asking the average value, you should remember the formula, and the formula is we actually measure the average of the half peak. So you can measure it. So this is 20, and you can say 20 over pi by 2. Bus, you put it and you can get the value. So it is going to be 12.7 volts. Okay. Now, another thing now it's coming here, the angle, which I already explained to you. Now, the angular measurement can be made either in degree or it can be in radians. Okay. So the angle is forms when the arc, so what is that? 1 radian means the angle is formed when the arc is equal to the radius of the circle. So, yani, this is called arc. See, this is called the arc. When this arc, yani this one, is equal to the radius, you know the radius, you know, the from the distance from the center to the periphery. So this, when they are equal, it is called the 1 radian angle. It is forming 1 radian angle now. So this is 1 radian angle here. They said like this. Okay, it is equal to now r, the radius of this one. So there are 360 degree or 2 pi radians in one complete revolution. Okay, and 1 radian is equal to 57.3. You don't need to remember this one. It's easy. You can see now. So girls, you can see here the cycles, the angle in the radians. As you can see here, the complete is starting with the 0 radian here, and it is completing 2 pi radians at the end, 2 pi. So see, this is interesting thing here. Maybe it's later on, not here. Okay. So like this mentioning the angle, this is pi, half pi, yani pi by 2, pi by 4. And if you want to represent in degree, you can also represent in degree. As I mentioned, this is 360, half is gonna be 180, its half is gonna be 90, its half is gonna be 45. Yani pi by 4 is 45, pi by 2 is 90, pi is 80, 2 pi is this one, and this is 3 pi by 2, which is 270 degree. So these are the different angles in radians and in degree. So see now, if we compare, so we start this vector from the 0 point. At this time angle is 0 degree, and we can say 360 also. Now if we move here, it is forming basically the angle. How much it is forming? 45, or I can say pi by 4 radian. 90 degree or pi by 4, exactly it is 90. From this 0, from here to here, it is 90. Now it's take complete revolution, and when it reach here again, so angle is now 360 or 2 pi. So like 0 or 3 pi value is gonna be same, because it reached to the same value which is started in the beginning. This is something, okay? Now there is a relation how we can convert radians into degrees. So if I give you angle in degree, girls, degree, you can convert it into radians. So put that degree here which is given to you, you multiply with this factor. What is that? 2 pi over 360. 2 pi over 360, and you know that this 2, if we cross this one, it will go half time, yani 180. So I can also write this formula this way. What is the way? That radians value is equal to pi over 180 degree multiplied by the degree. Also, if the angle is given in radian, I can convert it into degree. So this is the way to write it. So degree is equal to 180 over pi. Just you need to flip this one, and you can cross multiply in order to get the degree. So for the degree, 180 degree will be in the numerator, denominator will be having pi. While for radian, pi will be in the numerator, denominator it will be 180, and you will multiply with the degree and here radian. So this is the formula to convert degree into radians, angle, okay? So if I ask you how many radians are in 45 degree, so it's so simple formula, you know that the radians is equal to pi over 180 multiplied by 45. So you can get it this way. So the answer is here 0.75 radian. So here we can put the value of the pi, which is 3.14, and we can get the angle in radians, or sometime it comes in the pi form also. Okay, we can also write in terms of pi. All right, now how many degree are in 1.2 radians? So formula will be, because of the degree, the formula will be how much? 180 over pi multiplied by radian. But this is the way. So this way we can also find this one. Clear? Now girls, we are introducing new thing here, the instantaneous voltage. Yani, you know that this waveform is continuously changing with the time. As time is passing, value is not stable. It's keep on changing. It's keep on changing. So how can I know the value at each instant, or any instant, or any angle? For example, if I ask you at 0 angle, what is the voltage? So you can say 0. If I ask you at pi, how much is voltage? You can say 0. If I ask you at 90, how much is the voltage? You will say it is equal to A. But if I ask you at this angle theta, how much is the voltage? So it is difficult to identify this time, because I don't know exact value. So for that we have this equation which we call instantaneous equation. By the way, it is same if you want to write for the current. It will be I is equal to IP sine theta, and the voltage is given by this way. So this will help us to find the instantaneous value at the given angle. So VP here is the peak voltage, girls, which you can see here is mentioned A, or when we see the theta, so it's mentioned here theta. So given angle and given peak voltage, we can find what will be the instantaneous value of the waveform. Okay, see now, and theta could be in radians or it could be in degree because it's the angle. So if I ask you, if the peak voltage is 25 volts, the instantaneous voltage at 50 degree is how much it will be? So theta is given, peak value is given. You can just put in the equation and you can get it this way. How much it's coming? Can you check it? Sine 50. How much is sine 50? Get the value and multiply by 25. So you will get this value. Yeah, it is like 19.2 volts. So the peak value is 25, and 25 is at what angle? If you check it, it is at angle 90, correct? But it is below that one. 50 is somewhere here. So 50, we will be having less value. This is something. So now you can see this one, 19.2 is the answer. Now girls, it is the plot of the same question. You can see, so they are showing this is 90 angle. At this, the value is 25, yani peak. But 50 degree is the less than the 90. And at that time, what is the value? We can calculate it by the instantaneous equation. We can find it 19.2. It means is that if we draw a vector here, this is peak value vector and this is the angle theta. So it is there. So you know what happening? This vector can be drawn for corresponding value. So this is something. Yani if we change the angle, increase the angle, you see this the value will reach to the maximum value here. If we go further, so it is start reducing. So it can be considered as a rotating vector. See, I'll show you in the next slide how this vector is rotating, like here. So when we are, can you see the yellow point? This one, yellow dot. Yes. So it's showing, I am measuring here what is the value of the rotating vector. So this is a new thing which is phasor, which is helpful to understand. So the sine wave can be represented as the projection of the rotating vector. Okay, this is called vector. Now it is rotating at a constant rate. The rotating vector is called phasor. It is called phasor. So phasor are useful for showing the phase relationship in AC circuits. Now see, at 0, this is the phase relation. Yani angle is showing here 0. This is angle 90, 180, 270 and so on. So see what will happen if we change the point like here. So it is there exactly in the middle of 0 and 90, which is 45. So phasor will move here and you can check how much is the value at this time, like this one, right? Now, if we go further and you will see this one at this point, it is basically the angle is 90 because at 90, the peak value will be shown at that time. Now, if we go further, you will see the vector will go down and the angle is increasing, but the peak value is reducing now. Next, reach to 180, and 180 is basically the same point as the minima point. Yani 180, it is in the same line, but direction is changed, right? Now, next, now, next, now, next, now, next. So in complete 360 degree, this rotating vector complete its revolution and is reached to again 0. So this is called phasor, okay, diagram. And this is basically helpful to understand the relationship between two waveforms in the AC. Like here, you can see we have given two waveforms, A and B. So here we can find the relation between them depend upon the phase angles. What are these basically? The A is starting from the 0 point and completing one cycle. You can see here. B is starting, C is minima is here and maxima is another minima is here. So girls, what we can say, how can we find the relationship between them? So I can say A leads B. It's leading B by 90. Why? Because you see A is starting its minima here and B is starting its minima here. Yani who is advanced? Yani if this is also we say this is the time, so it is starting earlier, so it is advanced or leads, but it is starting lately. It is called what? Delay. So we can say that A leads B by 90. Also, I can say B lags A by 90. Both are same thing. Clear? Okay. Getting the point? See the another one, this example. So BA. Now look here. B is starting its minima more more early. And it is starting at the 0 again. So A is the reference again. So here I can say A is completing is one cycle here, but sorry, B is completing here and A is completing here, you can see. So I can say B leads A by 90 or lags B by 90. So phase angle is basically helpful to find the relationship between the waveforms with some reference. So A is the reference here. Based on that, we have found it like that. So let's see this example. Further example, yani the use of phase angle in the equation. So this phase angle now we can add in the equation itself. So this instantaneous equation with the phase angle, and this is what we call phase shift. Okay, so phase shift, yeah, I will give you, just wait, let me finish this topic, then we'll give you a break for the prayer. Yeah, because it's continuous, so let me finish this phase shift concept. So this phase shift is VP sine theta plus minus phi is there. So what is phi, girls? We added this one. It is a phase shift. So which will tell us whether the given waveform is, you know, advanced, yani leading or lagging with the reference, you know, this one. So we have added phase shift in this equation now. All right, see now. So here, example of sine wave that lags the reference. Which one is the reference one? You can see the reference is the blue one is the reference. Yeah, it's starting from the exactly 0, ending with 360 exactly. So we are going to check with the red one whether what is the relationship between them. So girls, when you see this one, it is starting at 45 angle and it is starting at exactly 0 angle. So you can see, you know, late. We can say this is late, or we can say reference is in advance. So late yani lag. I can simply say lag. This is the lagging. So I can write the equations. How can we write the equation? Do you remember the equation? This is VP sine theta plus minus phi. So it could be plus, it could be minus, you will see now. So VP, how much? 40. So it is gonna be 40 sine theta. And because it's starting exactly 0, so phi value is gonna be 0. So I am writing 40 sine theta. Now, if I wanna write for the red one, I will say V is equal to 30 sine theta. Now, we need to check whether it is positive or negative. You see, girls, because it is late. Understand? Because it is late, starting lately. Also, another point is that it is crossing the negative axis here. See, it is crossing negative axis, or you can say it is touching the negative voltage. So it is lagging. So it is gonna be minus 45. Why 45? Because it's starting at this point, 45. So I can write the equation for that, which is 30 sine theta minus 45. So we can say that the red one is lagged by the reference 45 angle. See now.
دكتور يعني
Notice.
مثلا next
See first this one. Just see this one first. So notice that lag sine wave is below the axis at 0. So the one which is lagging, you will find that it will cross the below the 0 point. Okay, so because it's crossing below the 0 point, you will find here the negative sign. You will find here negative sign, and the equations has a negative phase shift. So this is negative phase shift. So you will understand with the positive phase shift. Let's see the another example where the waveform is gonna be lead, this time lags. That's why negative phase shift. See now, this is waveform leads the reference. So you can see now red is gonna advance, starting more early. And how much early? You can see the angle mentioned here, 45. And it is leading, so it will touch the positive axis, not the negative axis, correct? So this is the point. How can you know whether it leads or lag? So when it is touching positive axis and the angle is given 45, so it is gonna be sine theta plus 45, which you can see now. So notice that leading sine wave is above the z-axis at 0, and the equation has a positive phase shift. Hope it is clear now. Clear? Leading and lagging. Okay. So this is the point. Now see this one and tell me what is the equation for all three waveforms A, B, C. What is the waveform for A? Equation, sorry. What is the equation for A? A waveform, then B waveform, then C waveform. It's mentioned, okay? Okay, one by one, okay? A, for the A first. So for the A, peak value is 10.
10 because the peak and sine.
Okay, theta.
Theta.
What about the angle? Where it is starting?
0.
Okay, so phase angle is 0. So can I simply say sine theta bus? Because phi is 0.
Yeah,
We can say
Phi is 0.
sin theta.
Yes. Yeah, phi is 0 bus. It's like that. Now, similarly for the B, 5 sine theta.
موجب 10.
Positive. How much? It is mentioned already angle. Yeah, positive 20. Correct. It is mentioned here. This one, because it's advanced and it is touching the cross upper, it means it is gonna be leading waveform, right? Similarly C. So for the C, it is gonna be 8 sine theta minus, correct? It is gonna be minus, and how much? You see where it is crossing this point, and which is mentioned already, minus 45, correct? So if I ask you which is leading, which is lagging, if we consider the A is the reference, so we can say B is leading because of positive sign, it is leading, and C is lagging with the reference. Clear to all? Yeah. Okay, this is the one. So this way we can find the relationship between all the waveforms. And you know this one, you are receiving mobile signals, right? And everyone in when you are in a class, in a crowded place, all is receiving signals. Same time it is transmitted, but how they are differentiated? They are differentiated by the phase angle. They are differentiated this way. All the signals are traveling same time, so that we can differentiate later on this one. This is the advantage of having phase shift. It's not like that at a time you can talk, other one cannot. If you are in a crowded area, all can talk at the same time. So signal is traveling in a way, each waveform is separated and is with an angle, basically. Phase angle is there. So that each and every one can be recovered its signal according to this angles and all. So we can differentiate each waveforms. So this is just an idea of phase shift. So now we can just have a break for the prayer, then inshallah we'll continue. So it's 4:10, we'll start exactly 4:20. Okay, 10 minutes break inshallah. After prayer we will continue this one. Okay, let's start now.
Yes.
Okay, so let's see here. So this is about the power in resistive circuits, resistive AC circuits, okay, alternating current circuits. So girls, hope you remember the formulas for the power. What was that? For the DC circuit, we use P is equal to V into I. We use either V square over R, or we also use I square into R. Three formulas for the power. These formulas are same in resistive circuits as well, provided you must know the DC equivalent values. And I already explained to you how can you get the DC equivalent value by taking RMS values, not the peak values. So we need to find first RMS values, then we can find the power. So the formula is same. P is equal to V into I, but it should be RMS values of the voltage and current. Resistance is constant value, okay, always. So this is the way. This way you can simply find the power in any AC circuits, okay, for same formula. Now, so you can just understand the concept. This is the DC power, DC battery, this an AC, alternating current. So this is the symbol. This is DC voltage source, DC voltage, and this is AC voltage. Okay, so what does it mean? If we have 170 peak value of the AC and we got its RMS value, we will be getting 120, and you know it is equal to 120 DC voltage. So if we apply 170 peak value to this circuit, or we apply 120 DC voltage to this circuit, the bulb will consume same power, because you know that 170 peak, when we convert into RMS, it means we are converting into equivalent DC, which is, you know, something like that. So 170 peak is basically equal to 120 DC. So that will give the same power to this bulb if we give DC or if we give this one. Okay, so just a reference to understand the concept of DC and AC. Now, if this question comes, guys, calculate the sine wave, the power, what power is dissipated in a circuit where peak value is given 40 volts and applied to 100 ohm. So we have given peak value. Okay, so what we need to do, girls? For the given peak value,
Find VRMS.
Yes, very important thing is you need to find the VRMS. If you are not finding, you will get 0. Without VRMS, it is just a DC value and it is wrong. Okay, so we need to find first VRMS value, which is, you know, that you can say VP over root 2, or you can multiply with this factor. Then after VRMS, you need to put this formula VRMS square over R, and you will get it. It is 8 watt. So this is 8 watt of the power will be dissipated in that resistance. Now, so guys, actually what happened in reality, you know, we have AC and DC both supply present in the circuit. So frequently DC and AC voltages are together in a waveform. Okay, so they can be added algebraically. When they are there together, they can add algebraically to produce a composite waveform. So here an AC will ride on DC level. So see here, earlier you have seen that we have drawn, this is the waveform, simple, okay, AC waveform, which is swinging around 0 point. But with the introduction of the DC and AC both in the, in the circuit, what will happen? AC voltage will ride over the DC level. So what will happen? This is the DC voltage now, VDC, and AC voltage will be now riding on the top here, or swing around the DC, and it is shifted above the 0 axis, and it is like that. So how can we find this maximum value and the peak value, or the minimum value? So it is what VDC plus V peak will give the maximum point, and VDC minus VP will give us negative point. Here we can see that VDC is larger than the VP, so all the waveform is above the 0 axis. Understand? Now, if the VP is larger than the VDC, so what will happen? Because it is short now compared to the VP, some portion of the waveform will be under 0 axis. You can see this time because of this one. So this is the formula to find the maximum value, yani VDC plus V peak and VDC minus V peak. And we can see here the shaded portion is under the 0 value. It is because of VDC this time is less than VP. Clear this point? Okay. Now, so see this one. So this is the circuit. Here we have both sources, AC source. You can see this is AC source. This is a DC source. And this is a circuit, simple series circuit, and resistance value is given here. So they are asking determine maximum and minimum voltage across the resistor. Now we have DC, we have AC. So both will be developed across this resistor. So how can we find the maximum value? Formula Vmax, VDC plus V peak. We will add peak value, not the RMS, okay? So 12 volts plus 10 volts, it is 22 volts. Now V minimum, VDC minus VP, which is like that, and 2 volts. So what will happen now? This resistance will having minimum value 2 volts, maximum value 22 volts. Now they are saying show the resulting waveform. So I can also draw that one. So this is the 0 point, and we will draw first a DC signal which is given 12 volts. Now the maximum value is 22, we already calculated. Minimum value is 2, we already calculated, and we can just draw it. And we can see it will always be above the 0 axis. It is because VDC is greater than V peak. This is 12 and peak is 10. That's why it is above the 0 axis. Okay. Otherwise, this another case it can be down. So we can also ask you draw the waveform. So you have to draw this neat waveform, not the rough. You just draw like this or say, okay, teacher, I'll draw. No, 0 marks. It should be drawn properly if the question comes. So you can have a scale, pencil with you so that you can show properly this way. Okay. Even it's not proper like that. So it's some scale you can assume and just draw it. So
Doctor, about V peak, I didn't understand the graph of it. How it is done?
Which one?
V peak.
So V peak is this one, nah? Vmax, which is 22. The V minimum is 2 volts. So what is the peak value? See this one, here is 22. And here is how much? 2. And from where you are measuring? From the 0 axis. So from here is 22. And it is from here, it is 2 bus. What is the difficult thing here? Just simple, you draw the waveform. It is gonna be sinusoidal and it is gonna be swing over the DC. This is DC voltage. And this is what? DC plus AC. This is what? DC minus AC. The same waveform which is shown in the previous slide. This is, but now you have values.
So
what is not
10?
clear? Huh?
10 refers to what? You said yes here.
What 10? 10 is the peak value. What is this one? Peak value.
Just
AC peak value.
Okay, I understand.
And this is DC peak value. Values are given already, na? This is what we apply here in the formula. What is that? 10. This is 10 given in the function. What is it, sir? Formula in the question. Okay, so this way we can draw this one. Now, next thing is pulse waveforms. Pulse waveforms. What is a pulse waveform, girls? Pulse waveform is basically can be described as a very rapid transition, leading edge from one voltage to the current levels or to the another levels. See this one and you will have clear idea. Next slide. So this is called pulse waveform. Pulse waveform yani it has a rapid transition. See here at the reach here, it is quickly changing its value and becoming high. For example, if it is 0 volts, it is reaching to the 1 volts very rapidly. See this one? So like practically it is not possible. Voltage can change from one level to another level in no time, quickly, suddenly, rapidly, right? So this edge where it is changing from lower to higher value is called leading edge. When it come back from higher, let's suppose this is 1 volts and the lower is the 0 volt, so it is now coming down. So this is called trailing edge or falling edge, and this is what we call baseline, and this is called the pulse width. So a pulse is what? It is a rapid transition of the values of from low to high. But see, this is ideally possible that it is in no time quickly change voltage from low to high or high to low. But practically, it always took some time to change the voltage from some low point to high or high to low. So actual pulses, however, are never ideal. Pulses cannot change from one level to another instantaneously. Time is always required for a transition or what we call a step, as illustrated in the next figure. Okay, so this is the positive going, girls. Positive going yani which is changing from low to high. This is negative going yani which is changing from high to low. This is high to low. This is low to high. This is something. Okay, this is called a positive going pulse. This is called negative going pulse, which is coming down from the high value. So this is two examples of the pulses, ideal pulses. See the practical pulses. So practically, it is not gonna change rapidly. It will take some time to reach the maximum value. So accordingly, we have some times definitions you will see now. So rise time, which is denoted by TR. It is the time required for the pulse to go from 10% of its amplitude to the 90%. Yani, if I say the amplitude is 1 volts, okay, so it is gonna be, or they are saying here A, so it is gonna be 0.1 A, yani here it is the 10%. Alhamdulillah. Okay, sorry. So it's the rise time, and this is the 90% of its value. So the time required to change the voltage. Okay, so 10% to 90%, this one. And how much this time is? This time is called TR, yani rise time. Similarly, we have fall time. Fall time is what? Whenever is change its value from 90%, okay, 90%, or if they are saying it is a, so yani 0.9 A to 10%, yani 0.1 A. So this is TF, okay, yani fall time. Okay, now third thing is come, which is pulse width. What is a pulse width? Pulse width is always measured at the the leading edge and trailing edge where its value is 50%, yani 0.5 A. So this is called the pulse width. You can see time between the points on the leading edge where the value is 50% of the amplitude, and the point of trailing edge where the value is 50% of the amplitude. So three definitions for the non-ideal pulses. Okay, in ideal cases you have seen that this is gonna be step change, yani quickly change, higher value, lower value, like that. Okay, but this is non-ideal pulses. So another thing is here added repetitive pulses. What is repetitive pulse? Repetitive pulse means periodic, yani which keep on repeating itself. So any waveform that repeats itself at a fixed interval is called periodic. So if you just focus in these waveform and just look this point to this point, yeah, and here, okay, just focus here. Can you see it? This is keep on repeating here, every T, capital T, here to here, it is again repeating, see, then here again repeating, then again repeating. So it is what? Repetitive pulses. Okay, so same for the next. So it is from here to here is the time period, and it is keep on repeating, same here. So different examples of the repetitive pulses. Okay, so this is where, what is T here? It is the time period, and it is completing a cycle, higher, lower, and this is finishing here, yani it is time period. Then again it is start here and finishing here, so it's called time period. And this is called the pulse width, yani the duration through which the pulse was high. If I say this is 0 volts, if I say this is 1 volt, so it maintains one for this duration. This is called TW, yani pulse width. Now, so an important characteristic of the periodic pulse is the duty cycle. So what is a duty cycle, girls? You will see now. Duty cycle is basically a ratio of pulse width, yani TW, to the period, which is T, and it is usually expressed in percentage. So I can say duty cycle is equal to TW over T, 100%, multiply this one. So you can ask, yani if TW is given, T is given, you can find the duty cycle for the given waveform. So let's see an example. So determine here the period, frequency, and duty cycle of the waveform. So can you find how much is the period? Period is what? The time which is repeating.
10 microsecond.
10 microsecond is the period, correct? So what about the frequency?
1 over 10 micro.
1 over 10 microsecond, correct. And duty cycle, 1 microsecond divided by 10 microsecond multiply by 100. It's like that. So it's so simple to check this one. So this is like that. Okay, we can find this way. So this type of questions are possible. You can easily find it. Now, so similar to that one, girls, now we have another non-sinusoidal waveforms. This is a square wave. What is a square wave? If you just look here, square wave is a basically pulse waveform which is having 50% duty cycle, yani half time is having half value, yani high value, and half time it is having low value. You can check it in the figure. So it is high here for the T/2 time period, and it is low, which is like if I say again, it is 0 and it is 1 volt. So it is made like that. So it is called a square wave, which have 50% duty cycle. All right. Now, another thing comes here, average value of the pulse waveform. What is the average value and how can we get it? So average value can be get by this formula. So V average is equal to baseline. Baseline yani where it is starting. Sometime it is at 0, sometime is above the 0 or below 0, which is like baseline. Plus you will add duty cycle, okay, without percentage, yani TW over T, and we multiply by the amplitude. And you know the amplitude, yani the distance here to here. By the way, this is a square wave, so it is gonna be same either here, here or any places. Okay, it's not a sine wave. So based on the average, the question may come. So determine the average of each of the positive going waveforms. So you can see the average they are asking. So formula is this one. First of all, check the baseline. Can you find the baseline, which is 0? Now duty cycle, TW. Yani you can say this much of duration, pulse is high. We called sometime high time or on. Okay, which is 1/10. When you say 1/10, it is 0.1. You multiply by the amplitude. Amplitude you can check from 0 to here. It is 2. You just put it there and get 0.2 volts. So this is the average value. Now, second waveform. So here you can see the baseline. You can see this is above the 0. So baseline is 1. All right. So put this one, duty cycle 0.5. How you will check the duty cycle, girls? Duty cycle is yani on time, this time, which is given 1. And how much is the time period from here to here? Because this is one cycle is completing here, and this is gonna be repeat. So 1/2 means 0.5. Multiply by 5. 5 is the amplitude, yani from here to here. 6 minus 1 will give you 5. You can get it. Now the third one is the baseline. See the baseline, which is negative. Okay. Now, and duty cycle, you can see this is the time period, complete time period 20, and on time is half because it's a square wave, you know that. So 10/20 will give you 0.5 duty cycle, and you will multiply by the amplitude from here to here. How much is the amplitude? It is gonna be 2. Just put the value and you will see it is 0. You know the reason? When you see it, it is exactly half above the 0, exactly half below the 0. So it is cancelling each other. Yani this negative cancel with this one. This negative cancel with this one. So that's why the average is gonna be 0. Similar to the sine wave, if you remember, for a complete cycle, it is gonna be 0. Okay, this is the reason. All right. So this way we can also find. So based on the formulas, girls, you can find the questions. Okay, other than this square wave pulses, we have different type of waveforms also, like a triangular wave. So what is a triangular wave? It has the shape of triangle, girls. See this one? So it is like that, In the lab, you can see this one. There is a function generator. Now you will be having experiment. It is generate this waveform. This is triangular. Okay, so this is a triangular wave composed of positive going and negative going ramps. What is positive going ramp? Yani this is called positive going, values increasing. Another is negative going ramp. This is negative going. This is positive going. This is negative going, like that. So it is a triangular waveform. Also, we have sawtooth waveform. What is sawtooth waveform? See here, positive going ramp, and for a long duration, which is T, but negative going is very short time. It is not exactly straight. You can see this is tilt. See this one, little bit tilt. So this is called sawtooth waveform. Okay, so for your reference, they are all alternating sawtooth waves. Now, triangular wave and sawtooth waveform. So it's some relation here, girls. So how we can find the slope? So this is the positive slope, and how can we find? It is basically voltage divided by the time. So it is here positive ramp. Now negative ramp, it is decreasing. So formula for the slope is same, minus. Why minus? Because of it is decreasing from the highest value with the time. So minus V/T, it is basically applicable for both either voltage or current, that ramps. Okay, so this is the triangular sawtooth waveforms and its ramps. So here we can also ask, what are the slopes of the voltage ramps given in the figure? So you know that it is a positive ramp as the value is changing from here to here. This is 10 volts divided by 5 millisecond. So it is gonna be 2 volts per millisecond. So this is the slope. Yani per millisecond, the voltage is changing 2 volts. Now here is negative because changing from high to low. So it is 0.5 divided by 100 millisecond. So minus 0.05 volts per millisecond. This is the slope of these Rms, which is given in the figure. Okay, so this is, we can find it. So up to now, is it clear, guys? Clear this one, this point also?
Yes.
Okay. All right. So we are just reaching to the end, and I believe this is the end, last topic of this chapter, which is harmonics. Do you remember in the beginning, I told you there was a statement which says sinusoidal wave is the fundamental wave and which is responsible to construct other waveforms. So now this is the point where I will explain you how a sine wave can construct another waveforms, as it is a fundamental, right? So now, so all repetitive non-sinusoidal waveforms are composed of fundamental frequencies and harmonics frequencies. So odd harmonics and even harmonics, there are two harmonics frequencies I will tell you now, and the fundamental frequency. See now. So if I have a waveform, its frequency is 1 kilohertz. Okay. So what are the odd harmonics? Odd harmonics are if I multiply this as fundamental frequency with the odd numbers. What are the odd numbers, guys? 3, 5, 7, 9. If I multiply with these odd numbers, so the frequency which I will be receiving, it is called odd harmonics of this fundamental frequency. Yani 3 kilohertz, 5 kilohertz, 7 kilohertz, and so on. Similarly, if I ask you what are the even harmonics, so if I multiply this with the even numbers, okay, so I will receive even harmonics. Yani 2 multiplied by 2, 4, 6, 8. So depend upon the fundamental frequency value, we need to multiply by the even and odd numbers, which will give odd and even harmonics. So in order to generate the non-sinusoidal waveforms, girls, we need two things. First, the fundamental frequency, and we need harmonic frequencies. Basically, we need odd harmonics. So I will show you now how can we generate the square wave by the help of sine wave. So even harmonics is given here. Now guys, see this one. So see this picture first, and in this picture, composite waveform. So here we have a sinusoidal wave. It is a composite of the fundamental and harmonic. So where is the fundamental? You can see here. This is the fundamental, the dotted. Focus here. Okay, this is fundamental. Now, what we are having? We have the third harmonics. And you know that as the frequency increases, it means more cycles within the same time period. So this is third harmonics. So it is completing here 3 cycles within the same time period. You can measure if you want to measure. 1 cycle, another cycle, third. That's why it is called third harmonics. So now girls, if you add fundamental and the third harmonics, what you will be getting? See here. So 0 plus 0, you will be getting 0. So green one is basically the sum. Now girls, you see this is the top value of the third harmonics, and when you add the same time the value, so this plus this will give you more value or not, which will be somewhere here, correct?
Yeah.
Sum will be larger. Now this is fundamental and harmonics is negative. So sum will be less than the fundamental or not? Yani we will receive this point. Getting?
Yes.
Okay. So when we sum fundamental and harmonics, so we will be getting the composite waveform, which is look like this one. You know, it's not sine wave now, but it is changed a little bit. Now, if I add more harmonics here, yani not only third, I also add fifth harmonics, then I've got the sum. So it will be something look like that, right? Now, if we add another few more, like fundamental, third harmonics plus fifth plus seventh, so it will be something more like that. Okay, so the dotted one, if you look here, it is a ideal square wave. Ideal. Practically, there are some glitches, some humps there. So if we add more harmonics, we will be more closer to this ideal waveform. So this way, with the help of sine wave, we can generate the square waves. Is it clear, guys? Getting the idea? How can we generate from the fundamental sine wave, the square waves? Okay. So this is for your knowledge. We are not going to ask you to draw something like that. So related to this harmonics, you can just consider as, you know, this one, this slide and onward. This is just an information for you. And now we have completed this chapter, and questions you can go through. It's so simple. You can find yourself answers. So you can check yourself. It's so simple. Okay. That's it. So we have done with this chapter. Clear? Any questions if you have, you can ask. I'm going to take your quick attendance, then I can leave you.